learning Rust pretty seriously. And this kind of brings me to why I started this project. And basically, I'd been using Apache Spark for a while. Spark's like a really cool framework. As I'm sure many of you know, it's implemented in Scala, which is JVM based. And some brilliant engineering has gone into Spark to kind of work around the fact that it's implemented in Java. So it has kind of kind of off-heap memory storage. It has code generation. There's lots of things to kind of work around the fact that it's running in the JVM. And I just thought, had this kind of hypothesis that if we were to implement something like Spark in this new Rust language, that it'd be, even a simple implementation would have pretty good performance. So I wrote this blog post in 2018, and I kind of started building this thing. The name's kind of changed along the way. It started out as DataFusion. I'm not going to get into that. So basically, I started building this thing in Rust. And early on, I was following Spark's model quite closely, where I was dealing with data as a row-based format, as opposed to columnar. And very early on, people kind of told me that it's kind of dumb these days to build row-based analytics engines, and that I should look at columnar. And this is where I discovered the Apache Arrow project, or kind of rediscovered it. I knew about it, but hadn't actually used it before. And Arrow seems like an ideal framework to use. It'd be great for interoperability with other systems. And the only problem was there wasn't a Rust implementation at the time. So very early on, I put together a very bare bones kind of Rust implementation of Arrow, which then got donated to the project. And since then, it's improved massively through other people contributing. So with that in place, I moved on to the DataFusion query engine, and then the Ballista distributed compute, which I'll be going into in this talk. But all of these projects are now part of Apache Arrow. So why Arrow? So basically, Arrow's been around for quite a while now, around 5 years, and it's been quickly becoming the de facto memory format for columnar data. I think most people are familiar with Parquet as a disk format, a format for columnar data that's optimized for disk. Arrow is that, but for memory. And there are lots of projects that use Arrow already, Dremio, Apache Spark has some Arrow in there for interop. Most of these systems have been around, they kind of predate Arrow. So most of the Arrow functionality is more about interoperability. I thought it'd be really cool to build a new platform to be Arrow native. I didn't have to design my own memory model. And as I mentioned, it'd be great for kind of interop with other projects. And of course, I'm not the only person who thought that'd be a good idea. There are a number of projects now that are being built from the ground up to be Arrow native. I won't go through them all, but a couple that stand out. So I happen to work at NVIDIA. NVIDIA has the Rapids QDF framework, which is actually a GPU DataFrame library that uses the Arrow memory format. Another notable project, Influx Data, are rebuilding the core of InfluxDB, actually based on DataFusion and Rust. And their project's called InfluxDB IOX. Definitely worth checking out. So that's kind of a quick intro into why Arrow. The next question, I guess, is why Rust? So I mentioned my background is kind of C++ and Java. And to me, Rust is like a good compromise between those two languages. It's compiled, it has similar performance to C++, but it has this really unique approach to memory management, which guarantees memory safety and guarantees that your code doesn't have any data races. So it doesn't have all the kind of the pain that comes with C++. And it doesn't have a GC garbage collector either, so you don't have those GC courses that Java's kind of notorious for. And basically, the compiler keeps track of your memory allocations and which thread has ownership over memory. And if you try and do something that isn't safe, your code won't compile. So incredibly frustrating when you're learning the language, but you soon come to really value that because it solves a whole category of runtime security and memory issues. On the downside, there is a steep learning curve still, even though it has got easier over time as the compiler gets smarter. But if you haven't already looked at Rust, I would highly recommend taking a look. What's wrong with Spark? I've already kind of touched on this. Because it's Java based, GC has a lot of overhead. The kind of dynamic interpreting of code has overhead, the bytecode. So Spark actually generates code and compiles it to work around some of these limitations. And it does a great job, but it would be much simpler, in my opinion, if we used a compiled language to start with. By the way, feel free to ask questions as I go through the presentation. So let's take a deeper dive into Apache Arrow. So I kind of mentioned it's a memory format, but what does that mean? So essentially, it defines the standard memory format for columnar data, and it consists of contiguous buffers in memory. So if you have, so really it's modeling arrays of data. So if you imagine you have an array of a fixed width type, like 32-bit ints, your data would just literally be a contiguous piece of memory. And to indicate which values are null or not null, you would have another buffer, which is a bitmap, basically. We would have one bit for each value, indicating whether there is a value or not. And then for more complex types like structs and maps, essentially you kind of nest these buffers to create those types. And the reason why you'd want to have columnar data in memory is that you can take advantage of modern hardware for processing it using a term called vectorized processing, which basically means you can leverage SIMD on the CPU, or you can use GPUs, which are fantastic at vectorized processing. SIMD, if you're not familiar with it, stands for single instruction, multiple data. So let's say you're adding two columns of numbers together. Instead of adding one pair of numbers, one pair with one kind of CPU instruction, you can use one instruction to add multiple pairs of numbers, maybe 8 or 16, and so on. So you get some really good speed improvements. So that's great within your own process. But then there's an IPC format. So if you want to exchange this data, maybe between Java and C++ through a JNI layer, or maybe between two separate processes, the great thing is you can just share a pointer to the data. You don't have to serialize and deserialize the data, but you do need to know, the receiving process needs to know what the data looks like. It needs to have the metadata for the schema. So the Arrow IPC format describes a flat buffer format for serializing metadata about the data. And because the metadata is pretty small typically, so it's quite a small overhead. And lastly, and more recently, there's a new standard called Flight. And this is a gRPC-based protocol, which basically brings the benefits of IPC to distributed systems. And that was something, that was one of the factors that kind of made it much easier for me to try and build a distributed system using Arrow. So that's the specification. And then we have implementations in many languages. There's like a dozen or so now. C++ and Java are the most mature. The C++ library is used. Other languages wrap the C++ library, like Python and R. So all of these libraries provide the memory format. Some of them provide computational kernels, so you can perform operations on this memory, on these data structures. And C++ and Rust are the only two that I know of that are essentially building query engines as well at this point. So looking at the Rust implementation in a bit more detail, I won't go through this whole slide, but there are representations for the different data types. So we have schema, field, data type. There are arrays and builders for building each type of array. There's a whole bunch of computation kernels, so aggregates, comparison operations, and so on. And this is all good for dealing with arrays of data. But if we're building like database-like systems, we need a tabular structure. So there's a record batch representation, which is a batch of data in columnar format. So really just an array of arrays and with a known schema. And then there are also I/O I/O functionality for reading and writing the formats you would expect. So CSV, JSON, Parquet, and you can also, of course, build your own data formats. So let's take a look at some code samples in Rust. So these are all like super simple examples, but this is how you would build an array of 32-bit ints. So you create a builder and you give it a capacity. So we're building an array of 5 values here. And then we can go ahead and append values or append nulls. And then we call finish to get the immutable array structure. And given some arrays, we can now do some computation. So here's a trivial example of a compute kernel. So here we have two arrays. We have A, which is an array of 32-bit int, and we have B, which is a Boolean array. And then we can call this filter kernel, and it will filter the integer array based on those Boolean values. So after we apply this filter, there are two true values. So we get an array of two integers out of this. Rust doesn't support object orientation. So this code sample kind of demonstrates that you can downcast an array to a specific type, assuming you know obviously you need to know the type, and that's where the metadata comes in. And this is the record batch structure I mentioned. So this is the tabular format. So it has a schema and then a vector of arrow arrays. And again, once you receive one of these, you can downcast the arrays, the columns to specific types. Okay, so that's kind of a whirlwind tour of Arrow in Rust. So let's look at DataFusion next. So DataFusion is an in-memory query engine built on the Rust implementation of Arrow, and it supports SQL and the DataFrame API. It uses the Tokyo async runtime. If you're not familiar with Rust, async is still relatively new, and Tokyo is one of the main kind of runtimes for async. And it actually makes it pretty easy to write scalable async multi-threaded code in Rust without having to take care of threading manually. And here's an overview of the DataFusion architecture. This should be pretty familiar to anybody working with query engines like Spark or similar systems. And so the user starts off either using the SQL statements or a DataFrame API. And what you're essentially doing there is you're building a logical plan for a query that you want to execute. And once you're ready to execute that query, it goes through an optimizer to produce an optimized logical plan, and then through a physical planner to get to the final executable plan. And along the way, there are various extension points. So you can provide your own custom operators, optimization rules, and so on. And InfluxDB are able to use this, for example, to build their new platform and provide their own implementations for kind of time series operations. So the DataFrame API supports kind of the typical things you'd expect to be able to perform a wide range of ETL functionality. So things like aggregates and joins and so on. And here's an example of using the DataFrame API from Rust. So we start off by creating an execution context, and then we can call methods on that context to build up our query plan. So here we're calling read Parquet, we're selecting some columns, then we have a filter. And at this point, we haven't actually executed anything, we're just building the plan. And the final line of code here where we call collect, this causes the plan to get kind of optimized, turned into the physical plan, and then executed. And you see the await on the ends there. That just means we're receiving a future for the results. So the thread we're running on will kind of be able to work on other things until the results arrive, thanks to Tokyo. And here's the same example using the SQL approach. So again, we start with an execution context. This will look very familiar if you've used Spark. This is where a lot of the inspiration came from. We can register a Parquet data source as a table on the context, and then we can go ahead and just use SQL to query that table. And again, we're just collecting the results here. We could also save the results to Parquet or CSV. You can also mix and match DataFrame and SQL just as you can in Spark. So you could create a data frame, register that as a table, then query it with SQL. So that's DataFusion. DataFusion was donated to Apache Arrow in 2019. And then since then, I've been working on and off. I've been working on Ballista, which is what DataFusion originally was supposed to be. And this is where the distributed aspect comes in. And, distributed is kind of hard. It took a while to get like a minimum viable product together for this. So this is the kind of grandiose architecture that I had in mind and still have in mind where I'd like Ballista to get to. This isn't what we have today, and I'll show the reality on the next slide. But the idea here is that on the right, we have the distributed cluster, So it could be running in Kubernetes, or it could be a standalone cluster. And we have one or more scheduler processes and some executors. We use the Arrow flight protocol so clients can talk to Ballista. So one thing that I was very careful about building this, even though like Rust is, I think Rust is a great language, I tried really hard not to make this Rust specific. So because of the use of the flight protocol and also using Google protocol buffers for serializing query plans, the idea is that you can have clients and executors in any language and have them interoperate. And this is really important if you want to have, for example, Java code or Python code as part of your pipeline. You want to be able to call that from the Rust executors. And then on the client side, so we do have a Rust client and Python bindings today. But the idea is that we should be able to build JDBC drivers and Spark connectors so that Ballista can kind of live alongside other frameworks. So this is kind of the reality today. So we have the Rust scheduler and executor, we have a Rust client, and we have Python bindings which map to Rust client. So you can build data frames in Python or Rust and execute them. Okay. So now let's go into kind of a bit of detail about how Ballista actually manages to run distributed queries. And this is really kind of the hard part. And this was very much inspired again by Apache Spark. And in particular, the adaptive query execution feature that Spark added in 3.0. So the way this works, so you have your initial query plan, the physical plan, and the partitioning can change at different points within your query plan. And when partitioning changes, you have to kind of shuffle data around before you can execute the next stage. So the basic approach here is that the planner will break the query down into these stages. And within each stage, the partitioning is the same throughout the operators in that stage. So in other words, they're embarrassingly parallel. Each query stage has a number of partitions that it can operate on, and you can run those in parallel in the cluster. Once a stage finishes, the results get serialized to disk, and the results actually get written out in Arrow IPC format. So that's pretty good because you don't have this SERDE overhead. The memory format is the serialization format, is the network format. So the next query stage that runs can very efficiently stream those results in and use them without SERDE overhead. And it also means that, theoretically at least, you could mix and match languages between query stages without overhead. One of the advantages of this adaptive approach is that once a query stage is finished, you have really accurate statistics about your data. Both like on a column basis, you'd know min-max values, how many null values, how many distinct values potentially. And for the query as a whole, you'd know like the row count and data sizes. So the beauty of this is that it then allows you to re-optimize the remaining parts of the query based on those statistics. So you could do things like reorder joins as one example. So this slide shows kind of at the protocol level how the query gets executed in this design. So the client submits a logical plan to the scheduler over the flight protocol. The scheduler will compile this into the kind of the physical plan, break it down into stages and tasks and partitions. And the scheduler will send these query plan fragments to the executors. The executors will run them and either store the results in memory or persist them to disk and temporary storage, or maybe write them out to Bucket as the final result. And once all of the stages are completed, the scheduler returns, or in fact, the client actually currently polls the scheduler to get the job status and see when the job's completed. When the job is completed, the client doesn't get the results of the query. It gets the metadata to know where to get the results from the cluster. So this is one really nice thing about the flight protocol, is that the client can actually stream the results in parallel from all the executors rather than funnel them through one process, as many systems do. That's pretty nice. So Ballista is incredibly new. It's something I've been working on kind of on and off in the spare time for a couple of years, but it only really became real early this year. And it kind of randomly got really popular on Hacker News. and there was suddenly a lot of interest and a lot of people using it and contributing. And so the very first release that was really usable was just in February, so just a couple of months ago now. And it allows you to deploy Ballista to Kubernetes, Docker Compose, or run a standalone cluster. You can run some real queries using SQL and data frames. And when I say real queries, I've been using one of the standard, kind of industry standard benchmarks for testing for functionality, and also just seeing how we're doing on performance. So the results currently are for relatively small data sets, like 100 gigabytes. Some queries are faster than Spark, some are slower, but we're kind of in the same ballpark. So at least it shows, it just kind of helps show, even though this is a very early project, there is some maturity there already. And to really make this work well, we know that we have to do some work to implement more scalable join algorithms, for example. So things like shuffle hash join, basically partitioned hash joins. So here are some results, and take these with a pinch of salt. These are very kind of informal. And again, this is really just validating that we're kind of on the right path with this. So this was using one of these standard benchmarks with 100 gigs of data. These queries have a lot of joins and aggregates. And this is comparing Spark version 3.02 with this early Ballista release. And as you can see, it shows that we're kind of in the same ballpark. Ballista was faster for some queries, slower for some others. And I kind of gave this slide the title "Relatively Fair Benchmarks," because Spark is optimized for big data, so this isn't really an ideal use case of Spark with just 100 gigs. But then there's a caveat to that. The way I think the description that I've heard that best describes, what does big data mean? I think it means you have more memory, more data than you can fit into memory. So, my laptop has 32 gig, 100 gig is kind of big data for me, unless I'm running on a cluster. And I think this is an interesting area for Ballista, and I hope it will scale well to big data in these huge clusters, but I also hope that it will scale down well. So this is one of the clusters that I'm currently testing on, which is a 32-core Kubernetes cluster running Raspberry Pis. So, pretty slow ARM processors, limited memory, and in this particular cluster, very limited bandwidth for disk I/O, because I'm using SD cards. So this will be, I don't have any results for this yet, but this will be kind of an interesting opportunity to see how well Rust can scale down, because Rust has like really great memory efficiency compared to a language like Java. So I'm kind of going, that's kind of the end of the slides, kind of went through those a little bit quicker than I hoped. But we've got time for questions if there are any. So it's just a shameless plug. I wrote a book at the start of the year as I was kind of designing Ballista and working my way through this. So it's just an introductory level book to query engines, but it does cover all aspects of how you would go about building a query engine from scratch, including like SQL parsers and query planning and so on. So the Arrow Rust project is split across 2 GitHub repos. We actually just had a bit of a reorganization recently where we moved out of the main Arrow mono repo. So go check those out. So it's GitHub, Apache, Arrow-RS, and Arrow-DataFusion. The DataFusion one contains DataFusion and Ballista. So definitely, if you're interested, take it for a spin. Let's find some issues you want to work on if you're interested in contributing, and I'll leave my contact details up there. So that's it. Thank you.
Okay, great talks. So, folks, if you have questions, you can put on the chat. So we can see the chat and then try to answer the questions. Andy, I just want to ask a clarification question on one of your benchmark comparison with the Spark on that graph. Is that 100 gig, 100 gigabytes of data for the Ballista? Is that all run 100 gig of memory running, or is it no?
So yes and no. So I guess computation is happening in memory, but the intermediate results between each query stage are persisted to disk. So yeah, Ballista doesn't have any support for out-of-core processing. So operations do have to fit in memory, like each task that's executed has to fit in memory right now.
I see. I see. Okay, cool. Thanks for clarification. I see somebody has posed a question. Let's see. What's the target audience for the project?
That's a good question. I guess people that are using systems like Apache Spark, but perhaps are looking for something more efficient in terms of memory usage, or being able to scale down to things like ARM processors, or really just people looking to kind of invest and help build the next generation of kind of distributed ETL systems. Because I think there's an opportunity here with Apache Arrow, because we kind of started with the Arrow memory format and everything's columnar. There is an opportunity here to build something that is just way more kind of performant and scalable and efficient than today's state of the art. But obviously, it's going to take a lot of effort to get this to the point where it has feature parity with something as mature as Apache Spark.
I see. Any other questions, folks? Another question coming from Jill. It says, I'm working on Scala now, but plan to move to Arrow Rust environment soon. Do you have any advice for someone with little experience? That's a good question. I want to ask the same question.
So the question is, any advice moving from Scala to Rust, I guess?
Yeah.
Yeah, it's interesting. I switched back, like Scala and Rust are the two languages that I use. Scala in the day job because I'm working with Spark, and Rust in my spare time. And it's funny, switching back and forth isn't too bad. The match statements are quite similar, the pattern matching. And Rust is kind of is quite a pragmatic language. It's not a pure functional language, but it does have some functional aspects. So often you're dealing with iterators and you're calling like map and filter and flat map, those kind of operations you would also use in Scala. So that feels quite natural. Where the challenge comes in, there are two big challenges that I've gone through. And it's object orientation and memory management. So Rust is not object oriented. And when you're coming from Java, as I was coming from like 20 years, predominantly Java, I kept trying to write things in an object oriented way in Rust, and it just made it really hard. And you have to just learn to use kind of composition instead. And the memory management is the big one. So in Java, you just create objects, everything's a pointer, the garbage collector will take care of it at the end, don't worry about it. And in Rust, you've got two choices. Rust gives you reference counted pointers, which gives you the benefits of Java, but with less overhead. So my recommendation when you're getting started is just to make use of the reference counted pointers. There are two types of reference counted pointer in Rust. There's RC and ARC. ARC is the atomic one, which you can share between threads. So yeah, kind of knock yourself out, go use those. When you're ready to get to stop relying on pointers and offheap and kind of heap storage, and you want everything super efficient and on the stack, that's where you need to get into Rust's syntax for explicit lifetimes. And I'm still not an expert on those. But if you're right, if there are parts of your code that's got to be super optimized to avoid accessing data on the heap, that's when you need to invest in learning about how to use the lifetimes efficiently. But in all of Arrow and DataFusion, I've pretty much managed to avoid almost completely. I've managed to avoid using explicit lifetimes, which are to me the really complex part of Rust.
Cool. I have a few more questions here. So, does it run its own resource manager, or can it operate with other resource manager directly? So you said that Kubernetes compose extra, but not sure if these are used, these orchestrators template to spin up a cluster, then Ballista will use what's there, or Ballista will talk to Kubernetes to get more resources. Not quite sure you get the question or not.
Oh yeah, that's a great question. And so I guess I'll answer like where Ballista is today. So because it is very early. So currently, as far as Ballista is concerned, it has its own scheduler and executor. The scheduler breaks down the query plan into the stages. The executors register with the scheduler and ask for work. So you can spin up new executors while a query is running and they will start participating. So it has that kind of dynamic scalability, but it doesn't work with a resource manager to do that scaling. You would have to do that yourself today. So you can deploy Ballista, say, as a stateful set in Kubernetes with like 2 schedulers and 8 executors. And then you can, if you scale up that stateful set yourself in Kubernetes and add more executors, they will start working right away. And the schedulers use etcd as a backend for storing, to keep track of all the stages and tasks. So there's redundancy as well there. So, and you can scale schedulers up independently. So there's a lot of kind of like pretty good architecture built in, but it isn't well integrated with resource managers yet.
Okay, so the next question is there a specification and or reference implementations for building language binding for Ballista?
So there are Python bindings in the DataFusion repo. So yeah, I mean, that's kind of the reference implementation. Yeah, I mean, I guess that's all we have so far. So Rust exposes a foreign function interface that can be wrapped easily in other languages. So yeah, I'd say the Python bindings are the reference implementation for that right now. And in DataFusion, it's even possible to run Python code as part of your DataFrame operations. And in theory, that should be easy to get that working with Ballista as well, but we haven't done that yet.
Okay, so I guess that's the question so far. So yeah, this is great. So let me well, just maybe waiting for a minute or two for others to think about questions. Maybe I'll ask my question myself. Suppose that I'm saying, hey, I like you on the daytimes we're using Scala and writing Spark jobs and for our daily work. So when do you see a point where we venture to say, okay, let's try using Ballista?
Yeah, that's a great question. So Ballista, again, it's super early on, and although it can run some pretty good queries, yeah, I mean, it's very, very far from something like Apache Spark that's been around for more than a decade with thousands of contributors. So what I think my hope would be that if I were running pipelines in Spark, like in my day job, I think I would be looking for opportunities to offload like small parts of those pipelines into Ballista to try them out, and then kind of interoperate back with Spark. Spark already has some Arrow support, so it seems like it would be feasible to build a Spark connector that could kind of work alongside Ballista, though I haven't worked out the details of that. So that would be the area where I would be looking to. I think that'd be a good way to try and get a bit more traction with Ballista.
I see. So for example, if I have a tiny Spark pipeline and I have a Hive metastore and I have this schema already, so I probably just use a Ballista to read the data from the Parquet and write back to Parquet, and then repair the tables. Boom, I probably get something, right?
Yeah, absolutely. You could do things like that, and if you yeah, and I guess if there are specific steps in your ETL process, you run some steps in Ballista, but yeah, where you're starting from Parquet, ending with Parquet, or starting from CSV, ending in Parquet. So you could run that in Ballista, and then your next piece of computation, maybe you need streaming and ML, you could run that part in Spark. So yeah, maybe a good place is for Ballista to start with some of the kind of ingesting data, or kind of that early kind of ETL to get the data in a good format for Spark to use.
I see. Cool. I see this here. Oh, somebody asking, how do you come up with the name?
The name?
Yeah, the project.
Oh, wow, this is the first time I've been asked this. That's really cool. So let me get my memory straight on this. So I was watching Game of Thrones, and so there's a few things here. So Arrow, Game of Thrones, the arrows, they're trying to kill this dragon, and they had these ballistas, which are the like these huge crossbows that were shooting the arrows to kill the dragon. And I was watching that. That's kind of where the name came to me of Ballista. I was looking for something arrow related.
That's pretty cool.
I'm glad that came up.
Okay. So if you folks don't have more questions, I mean, Andy, you want to have the last word?
Sure. So yeah, I mean, like really appreciate this opportunity to kind of spread the word. Yeah, it'd be great if people go check out the project. Maybe just try running it in some of your own data, find some bugs, file some issues. Or if you're looking for an opportunity to learn Rust, there's a really great community behind the project, not just Ballista, but DataFusion and the core Arrow libraries. So yeah, come join the fun.
How people can contribute into this project?
So the best place to start would be to go to, we use GitHub issues, and we do have a label for good first issue. So if you go look at that label, you'll get a list of issues that we're looking for help with. Some of them like really simple things like documentation help, others are like bug fixes. So that's a great place to get started and to kind of get to know the people and the kind of the process we use for contributing.
Great, great. Thank you so much, Andy. This is a great project. I'm pretty excited about this.
Sure, thank you. This is a lot of fun.
Would you mind to share the slides with the audience, with the members?
Yeah, absolutely. What's the best way? I guess I'll email them to you.
You can send me the link for the slides or just the deck, and I'll just I'll share it on the meetup with the members. All right. Thank you so much. Thank you everyone to joining. Yeah. So there's somebody. There's somebody asking, is there a Slack channel or Discord channel for the project?
There is. So there is the Apache Software Foundation has a Slack channel. There are links to it in the Arrow DataFusion repository in the README somewhere. But if you track down the ASF Slack, we're in the Arrow-RS channel in there.
Okay, great, great.